Quantum computer reverse time. Physicists use a quantum machine to reverse time on the smallest level. The arrow of time is quick to take for granted, but the gears of physics really work in reverse just as smoothly. After all, maybe this time machine is possible. An experiment from 2019 reveals just how much wiggle room we can expect, at least on a quantum scale, when it comes to separating past from future. It does not encourage us to relive the 1960s, but it may help us understand why not. Scientists from Russia and the US have joined up to find a way to crack one of the most basic energy laws in physics, or at least bend it down. The second law of thermodynamics is not so much a rigid rule as a guiding principle for the universe. This says that, over time, hot objects get colder as energy transforms and spreads from places where it is most powerful. It's a theory that explains why your coffee isn't going to stay hot in a cold house, why scrambling an egg is easier than scrambling it, and why no one will ever let you patent a perpetual motion machine. It's also the closest we can come to a law that asks us why we can recall what we had last night for dinner but not recall next Christmas. That law is closely related to the notion of the arrow of time, which posits the one-way path of time from past to future, said the Moscow Institute of Physics and Technology's quantum physicist Gordy Lasovic. It is possible to reverse nearly every other law in physics, and still make sense. For instance, you could zoom in on a pool game, and if you happen to see it in reverse, a single collision between any two balls won't look odd. On the other hand, it would be a sobering experience if you saw balls roll out of the pockets and reform the starting pyramid. This, for you, is the second rule at work. On the macro scale of omelet and pool games, we shouldn't expect anything in the thermodynamic laws to offer. But as we concentrate on reality's tiny gears, single electrons, in this case openings, emerge. Electrons aren't like tiny billiard balls, they are more like space-occupying stuff. Their specifics are determined by something called the Schrodinger Equation, which is a wave of chance describing the possibilities of the characteristics of an electron. If this is really confusing, let's go back to imagining a pool game, except this time the lights are off. You start with the information in your hand, a cue ball, and then send it rolling over the table. The Schrodinger equation tells you ball is rolling around at a certain pace somewhere on the pool table. The ball is, in quantum terms, at a bunch of speeds everywhere. Some are more likely than others. You can reach out your hand and grab it to mark its place, but now you are not sure how quickly it was going. You could even gently brush your finger against it and know its speed with certainty, but where it was going? Who doesn't know? There's yet another trick you might use. After you send the ball rolling, a split second, you can be pretty sure it is still moving at a high pace near your side. In one way, the Schrodinger equation for quantum particles predicts the same thing. The possibilities of the locations and velocities of a particle increase with time. However, Schrödinger's equation is reversible, said the Argonne National Laboratory materials scientist Valery Vinokur in the US. Mathematically, it means that the equation must define, under a certain transformation called complex conjugation, a smeared electron locating back into a small region of space over the same time span. It's as if your cue ball was no longer spinning across the dark table in a wave of potentially infinite places, but rewinding back into your pocket. In theory, there is nothing that prevents it from naturally occurring. However, you would have to look at 10 billion electron-sized pool tables every second in our universe's lifespan to see it happen once. The team used the undetermined particle states in a quantum computer as their pool ball, and some clever computer engineering as their time machine, instead of passively standing around and watching funding trickle away. Each of these states, or qubits, was arranged in a simple place that corresponded to a hand holding the ball. Those states rolled out into a variety of possibilities until the quantum computer was set into motion. By tweaking certain conditions in the configuration of the machine, these possibilities were limited in a way that intentionally rewounded the Schrödinger equation. This is exactly what happened in about 85% of trials focused on only 2 qubits. On a practical level, the algorithms they used to manipulate the Schrödinger equation into rewinding may help improve quantum computer accuracy. It is not the first time that this team has given a strong shake to the second law of thermodynamics. They enmeshed some particles a couple of years ago and managed to heat and cool them up in such a way that they acted effectively like a perpetual motion machine. Finding ways to push the limits of such physical laws on a quantum scale might just help us understand better why the universe flows as it does.